Hi everybody and welcome back. In this lecture, we will evaluate our cardiac detection model. Before starting, let us quickly import matplotlib.pyplot and matplotlib.patches. At first, let us define the device we want to work on. We use torch.device, which is either CUDA:0 if torch.cuda.is_available is true, else we work on a CPU. Now it's time to load our model checkpoint. We use our cardiac detection model .load_from checkpoint, to which we pass the path to the checkpoint. PyTorch Lightning typically stores the checkpoints in a directory of the logger. In my case, this is logs/default followed by version_1. However, if you ran the training more often or less, your version number might differ. In this directory, you should find a folder called checkpoints, which contains the 10 best checkpoints according to the validation loss. Let's use the last one. After loading the checkpoints, we set our model to evaluation mode, and last but not least, copy it to the corresponding device. As usual, to prevent PyTorch from printing the model structure, add a semicolon after model.eval and model.toDevice. Now we compute a prediction for all validation samples. At first, we define two empty lists called breadths and labels, which will store our predicted and ground truth bounding box coordinates. Next, let us use with torch.no_grad to prevent PyTorch from storing the gradients. Now we extract the X-ray images and corresponding labels by looping over our validation dataset. At first, we move the data or X-ray image to our previous defined device, convert it to float, and add the channel dimension. After that, we can directly compute our prediction, remove the batch channel dimension, and copy the result to the CPU if necessary. Last but not least, we append the current prediction to our breadths list and also the corresponding label to our labels list. Last but not least, we use torch.stack to convert our breadths and labels lists into a torch tensor. Let us now run this cell to finalize our evaluation. We can now compute the mean deviation between prediction and labels for all four coordinates. To do so, we compute the difference between breadths and labels, convert this resulting tensor to absolute values to finally calculate the mean along the first axis. This results in 4 values describing the mean difference between prediction and labels. That means that the mean difference for coordinate x0 is 4.7 pixels. For y0 it's 4.9 and so on. Overall, we can say that approximately we are 4 to 5 pixels off. This corresponds to an error of 2 to 3%. That's a very good result, especially considering the fact that our dataset was extremely small. Our cardiac detection model is able to accurately predict the position of the heart in X-ray images. Awesome! Let's finalize this lecture by plotting some results. At first, we define the index of the image we want to inspect. Let's simply use 0. Next, we can use this index to extract the image and corresponding label from our validation dataset. Additionally, we can extract the corresponding prediction from our pre-computed predictions. Let us now use a 1x1 plt.subplots to visualize the X-ray image with its predicted bounding box. At first we plot the X-ray image, remove its channel dimension and set the color map to bone. Next, we create the bounding box object by using patches.rectangle, to which we at first pass the coordinates of the top left corner defined by the first and second values of our prediction. Subsequently, we need to compute the width of the bounding box by subtracting the first element of our prediction from the third, and last but not least, the height by subtracting the second from the fourth one. Additionally, we set the edge color to red and last but not least, the face color to none. Now all we have to do is to add this patch to our axis object to inspect our result. Oops, let's quickly fix this typo, and here we go. Perfect! The bounding box matches the position of the heart. Let's take a look at another example. Absolutely perfect. And last but not least, once more with index 20, we observe again a really nice prediction. Congratulations! You successfully created and trained a model capable of cardiac detection. In our next project, we will automatically segment the left atrium in cardiac MRI images. Thanks and see you soon!